In this session, that is the third session of the coil springs, unit 6, the last unit of design of machine elements for 5th semester automobile engineering. We will do few more problems on coil spring or helical spring along with MCQ. Problem number 1. Design a wall spring of petrol engine for the following operational condition. Spring load when the valve is in open, that is the maximum load 400 Newton. Spring load when the valve is closed 250 Newton. Maximum inside diameter of the spring 250 mm. The length of the spring when the valve is open 40 mm. And the spring when the valve is closed 50 mm. Maximum permissible stressor 400 megapascal. Write down the data given. So here we will find what is the mean diameter and wide diameter of the coil spring. That is inside the diameter of the coil spring is given 25 mm, and which is nothing but mean dia is equal to inside plus small d wide dia, that is 25 plus d will be the mean dia. Since the diameter of the spring wire is obtained from the maximum spring load, thus maximum twisting moment of the spring is given by T is equal to F1 into D by 2. F1 is 400, D is 25 plus small d divided by 2. We'll have the answer 5000 plus 200 D. So this torque is also equal to, because the wire is considered shaft, so this can be also equated to equation for shafts, that is pi d cubed by 16 into tau from design data handbook of the chapter shaft, equation number 3.1 for solid shafts. When you compare both, you will have 5000 plus 200 d is equal to 78.55 d cube, and that becomes an equation of power 3, which can be solved by trial and error method. Just to minimize the value of d cube by just dividing 78.55 throughout the equation. We will have finally 63.65 plus 2.54 d is equal to d cube, and go on substituting the value of wire dia, that is small d, starting from 4, 5 like that. It is a trial and error method. Both the side the answer should be equal. Finally we will have an answer equal to be so 4 at wire dia 4.2 mm, nearer equal to 24.21 or 1, thus we will adopt 4.2 mm. After getting wire dia, we obtain mean dia, which is nothing but 29.2 mm. From these two equations, we have to go by one more equation, that is 11.1, where shear stress is given by 8 FD K by pi d cube. So here the wall factor K can be calculated by the equation 4C minus 1 by 4C minus 4 plus 0.615 by C, equation 11.2b of page the design data handbook Mahadevan, having page 139. So now when you see the value of C, which is already we have taken capital D and small d, previously we have calculated having capital D is equal to 29.2 and small d is equal to 4.2. When you substitute the value, you will have C is equal to 6.95. Now you put the value in the stress factor equation to obtain K 1.214. Then tau is equal to 8 FC K by pi d square can be considered, and F value will be 400, C value 6.95 into 1.214 is stress factor by pi d square, so that we can have D value, D is equal to 4.63. So here when you see that we are doing for two different readings. Initially we have already taken y dia as 4.2. With that help we have considered mean dia and then we have calculated spring index, then substituted in the equation, concerned equation, and to obtain once again the y dia. Why? We have to comparing both the values, whichever comes greater or bigger, that to be considered. Okay, when you see this, the later data gives you bigger value than the former one, so the y dia instead of 4.2, now you have to take 4.63, and the mean dia changes to 29.63. After getting 29.63 for mean dia and y dia 4.63, you calculate outside dia, which is 34.26 mm. From this we go to calculate the number of turns. So to obtain number of turns we have to go for deflection equation. So to have deflection equation, we want deflection at least given and take it, but here he has given in the some another fashion, that is the length of closed spring when valve is closed and length of spring when valve is open. So you just differentiate, you will get a deflection, that is 50 minus 40 will be 10, and that is the deflection. And spring is also given for open and closed valve. 400 minus 250 will have 150 load. So after getting this deflection and load, substitute the value in the equation of deflection, that is 11.5a, to obtain number of turns. That is deflection is equal to 10 is equal to 8 into 150 into 29.63 cube into I divided by 80 into 10 raised to 3 into 4.63 over 4. So the answer finally obtained will be 12 numbers. After getting number of turns, we have to get total number of turns, that is given by I plus 2, which is nothing but 14 numbers or 14 turns. Then find the free length of the spring. To obtain free length of the spring, the deflection for 150 for deflection 10 mm for 150 Newton load, the maximum deflection of the for the maximum load deflection what we have is for 150 load, that is 10 mm, but for 400, that is the maximum load. To maximum load the deflection will changes, that is nothing but the delta max is equal to 10 into 400 by 150, which is nothing but 26.67. then you use the equation for length ILA is greater than or equal to I plus 2D plus Y plus A, where Y is deflection and A is 15% of deflection. Now substitute the value to get the length 95.49. After getting length, you go for finding pitch of the coil, that is nothing but free length by I T minus 1 is total number of turns. So from this we will have 7.34 mm. Completes our first problem. Coming to the second problem, design a compression helical spring to carry a load of 500 Newton and with the deflection of 25 mm. The spring index may be taken as 8. Assume the following values for the spring material. Permissible shear stress 350 megapascal, modulus of rigidity 84 kilonewton per mm square, and Wahl's factor K is equal to 4C minus 1 by 4C minus 4 plus 0.615 by C. So write down the data and just substitute the values to have the dimensions of the spring. When you substitute K and C in the equation for shear stress, we will have D square is equal to 34.41 and finally Y dia is equal to 5.89 mm. By multiplying with the C, the spring index, mean dia can be 46.88 mm. And then outside diameter seems to be 52.74 mm. Now we have to calculate what is the how many turns are there for this design. To have the deflection is equal to 8f d cube I by gd power 4 in the equation 11.5a of design data handbook. Just substitute the values to get I seems to be 6 number, and the total number of turns in is given by the equation. I total is equal to I plus 2 is equal to 8 numbers. Then free length of the spring is given by I is equal or greater than I plus 2 LA is equal or greater than I plus 2 D plus Y plus A. That is 11.2 A. So after substituting value of Y and A, that is the clearance 0.15 Y, will have IA is less than greater than or equal to 6.2, sorry 6 plus 2, that is I is LA, length, free length of the spring. LA is equal or greater than, yes, we have to consider equal or greater than also, but better consider equal, that is equal to 6 plus 2 into 5.86 plus 25 plus 15% of 25, totally it becomes 75.63. So after having this, we go for pitch of the coil. It is given for free length by I total minus 1. I total is 8 minus 1 divided by 75.63 divided by 7 is 10.8 pitch of the coil. One more problem, that is design a helical spring for a maximum load of 1000 Newton for a deflection of 26 mm using the wall of the spring index as 5. The maximum permissible shear stress for the spring wire is 410 megapascal and modulus of rigidity 82 kN per mm square with considering Wahl's factor. So write down the data and better find the Wahl's factor. After finding the Wahl's factor, we will go through shear stress and deflection. So first we will go shear stress 8 of d k by pi d cube, and substitute all the values to have d square, that is 6.37 is the answer for y dia. Then finally so we will have mean dia by multiplying with c, that is nothing but 31.85, and we will calculate d naught equal to d plus small d, that gives us 39.22 mm, that is 31.85 plus 6.37, when you add it will have 39.22 mm. After getting this, we will go for number of turns to be calculated by the help of deflection equation. The deflection equation is given by delta is equal to 8 f d cube I by GD4. So d cube by capital D cube by small d power 4 is given by C cube by D, as you have that one, or you can use d cube by small d to the power 4 also to obtain I, that is number of turns. Finally the number of turns comes to be 14 after substituting all the values, and total number of turns is equal to 14 plus 2, that is equal to 16 turns. So finally we will calculate free length of the spring, that is given by LA is greater than or equal to I plus 2 D plus Y plus A. So I is 14 plus 2, that is 16, into D is 6.37, that is so Y dia plus 26 is the deflection plus 15% of the deflection gives you 131.82 mm. Then pitch of the coil is given by free length by I total minus 1, which is 131.82 divided by 15, nothing but 8.78 mm. Let's complete the problem, and coming to MCQs, the spring used in automobile car is coil spring, torsion spring, rubber spring and leaf spring. Basically here nowadays we are using coil springs. Actually it was both coil and leaf, but nowadays it is totally independent suspensions will there, so it is a coil spring in cars. If spring index is equal to 2.5, what can be what stress in the wire? They are high. They are high. In the closed coiled helical spring, the spring index is given by C by D. D is the diameter, mean diameter, and small d is the wire diameter. Respectively, for considering the effect of curvature, the wall factor for K is given by 4C minus 1 by 4C minus 4 plus 0.615 by C. That is, the answer is B. After this, you go through the problems and do it, practice it, thus thanking you.